Good afternoon. This is our narrated version of the PowerPoint for faults, earthquakes, and mountain building, crustal deformation. Except that for the most part, we will leave alone the mountain building and crustal deformation as we rarely have time to cover it. So it's no longer chapter 6. That is from a previous textbook. I think it's chapter 8 in our current textbook, the Marshak textbook. All right, so our opening slide here, what we're looking at are images from the Kobe earthquake that happened in Japan back in 1995. So this was only a 6.9, but I believe this had a relatively shallow depth. And look at these images here. You can see these buildings in various states of collapse. So on the top left there, that reddish color building, we call that pancaking, when the different stories of the building all collapse together, and that's a terrible thing. It's very hard to survive something like that. Take a look at the image over there on the right. That's a double-decker roadway, and of course you see clearly what has happened to the top deck is now over on its side, and that's not the worst case scenario. I mean, that was better than having it pancaked. Looking back over to the images on the left again, how about the bottom left image? Look at that building there. It looks like it's just basically come up off the foundation and is now laying over on its side. That is something that we might expect from liquefaction. Here we're looking at images from the Haiti earthquake. This is back in 2010, and I happen to know that this is the presidential palace there in Haiti, and the only reason I know that is one of my former students a few years ago. He was in the Army, or he had been in the Army, and he was in the Army back when the Haiti earthquake happened, and his unit was sent to Haiti for some number of weeks or months to help out. All right, so as we discussed in class, for those of you that were able to come to class, the first bullet here is something you want to write down. What are faults? Well, they're basically just big fractures or cracks in the ground that accommodate movement as the plates are moving around in relation to each other. So these fractures that are faults are usually, they can be quite large and extensive. The San Andreas Fault, for example, is about 800 miles long. And just so you know, not all fractures are faults. Remember back when we learned about sedimentary rocks and physical weathering, we talked about joints that are just fractures in the rocks. So not all fractures are going to be faults. This picture we're looking at here is a really good image of the San Andreas Fault trace in an arid region of California. And here Wallace Creek has been offset by about 100 yards or 300 feet. This took, of course, several earthquakes for that offset to occur. So if you were in class, I asked you to write down both of these bullets here. So what exactly is an earthquake? I mean, we know what an earthquake is. If you say, you know, what's an earthquake, or can you imagine an earthquake? Everybody can imagine images they've seen on news or in movies about earthquakes that have happened. So it's ground shaking, and there are many things that can shake the ground, including on an upcoming slide, we will briefly discuss all the things other than slip on a fault that can shake the ground. But what is it that's causing the ground to shake? So partly it's due to rocks being broken as you have movement, slip, and offset all on the fault plane. And this is occurring in the brittle realm. So yes, the rocks are breaking, but we will see on a later slide that part of that energy is being released due to something called elastic rebound. But we'll get into that later. And of course, the energy released from movement on a fault is going to travel outwards from the focus in the form of seismic waves. And we've already learned a little bit about the body waves, which are the waves that travel through Earth's interior, the P waves and the S waves. Remember that the P waves can travel through solids and liquids, but the S waves will only travel through solids because the S waves travel in a shear motion, and the outer core is liquid, and liquids do not have shear strength. Also remember, this is how we discovered that the outer core is liquid. So many things will shake the ground and register on a seismometer. You know, most of the time it's going to be that first bullet there, slip on an existing fault. But, you know, here and there new faults are formed. Even the San Andreas Fault hasn't been there forever. It's maybe been there for about 28 million years. As we discussed with Mount St. Helens, shifting magma in a magma chamber can shake the ground, as can the force of the eruption itself. Large landslides, meteorite impacts. Meteorite impacts, I guess maybe that's part of the reason we don't have an upper limit on the Richter scale. The largest earthquake that we've ever recorded in modern times was a 9.5, and that was back in 1960, and that was in Chile on the west coast of South America. But big meteorite impacts could go way higher than 9.5. And of course, sometimes it's man-made activity like coal mine explosions, underground nuclear bomb tests, and hydraulic fracturing. There's a lot of earthquakes out in Oklahoma due to hydraulic fracturing. Okay, focus and epicenter. If we were in class together, I would ask you to write down both bullets here. So the focus is the exact location along a fault plane where your earthquake is going to occur, where rupture and slip occur. In parentheses, I have or begin because in some cases, like earthquakes along strike-slip faults, you might actually have offset along many, many miles of the fault. So back in 1906, when the Great San Francisco earthquake happened, we had offset on about 600 miles of the San Andreas Fault. So if there's a lot of offset, if it occurs over a large area, then the focus is simply where it begins. And then, of course, the epicenter is the point on the ground surface that is directly above the focus. Some textbooks might refer to the focus as the hypocenter. That is, of course, also correct, but we're going to use the word focus. And you should have heard this term epicenter before. Every time there's an earthquake, they're going to report where the epicenter is. And, of course, that's where you're going to have the most ground shaking and the most damage. Here's a 3D drawing of the focus where your small earthquake has happened on a sloping fault plane, and then of course the epicenter on the ground surface above. And then those concentric circles are just simply denoting that you have P and S waves leaving the focus, traveling outwards in all 360 degrees. Here's another 3D drawing showing us the focus and the epicenter. Okay, so by the way, as I record this, and this is fall of 2020, one of our COVID years. Anyway, just 2 days ago, there was a large earthquake that hit in the Aegean Sea, very close to Turkey, and it shook Turkey quite a lot and Greece as well. And they're showing damage from this on the Weather Channel right now as I record this lecture on earthquakes. All right, back to the slides. So fault planes, as we have shown in class with drawings on the board and with the block diagrams, some fault planes are going to be vertical or nearly vertical, you know, pretty close to 90 degrees straight up and down, and our strike-slip faults are going to be vertical. But most faults on this planet are going to slope at an angle. By the way, there are 3 video lessons already on Canvas that go through the different types of faults, hanging wall and footwall, focus and epicenter, fault trace and fault scarp, and there's even 1 or 2 short videos where we show or demonstrate the faults with the block diagrams for people that are in quarantine and did not get to come to class. Okay, since most faults slope at an angle, that means that our sloping fault plane is going to bisect the rock into 2 different blocks. You've got a block of rock above the sloping fault plane. We're going to refer to that as the hanging wall. And then you have a block of rock below the sloping fault plane, and we're going to refer to that as the footwall. Okay, so hopefully you made it to class and we're in our group discussion on trying to learn the difference between hanging wall and footwall. If you are not, then you want to watch the video lessons and just try to pick this up on your own. But the image on the right is very simple. So the top of the gray, of course, is the ground surface. That black line at an angle is the fault trace, or sorry, the fault plane. And then you'll notice that the block on the left is actually above the fault plane. That's why it's labeled hanging wall. And then the block on the right is below the fault plane, and that's why it's labeled footwall. Now over on the left, we have a nice 3D drawing showing our sloping fault plane. In this case, the image on the right, the hanging wall is the block on the right. It is above the fault plane, and the footwall is the block on the left. It is below. And we've had some offset here, haven't we? So look at the yellow. We're going to say that's a layer of sandstone that has now been offset by movement on this fault during this earthquake. So how might we describe the movement of the hanging wall? The hanging wall here has dropped down relative to the footwall. It's also a good time to introduce fault trace and fault scarp. Okay, so in this drawing it's labeled fault line, and that's not incorrect. The fault line and the fault trace, they mean the same thing, but I'm going to use the term fault trace in the class and on the exam. So anywhere that your fault plane intersects the ground surface, if it intersects the ground surface, we're going to call that a fault trace. And if you have had movement on this fault that dips at an angle, well, that's going to give you some kind of vertical offset on the ground surface, and we call that a fault scarp. A couple of pictures here of hanging wall and footwall in the real world. The image on top is a road cut. What do we mean by a road cut? Well, we've been using this term before in class. So a river cuts through a mountain and makes a valley, and Department of Transportation knows that that's a great place to put a road to cut through the mountain. So they blast away on the sides and they make it a little bit wider, and then they put in a road. Well, the geologists love this because now we have, basically a cross-section view into the shallow subsurface. They're very easy for us to see on the side of the road. So notice the two arrows there. Okay, and your hanging wall and footwall are labeled, and that's okay. This is just for practice. But hopefully you can clearly pick out, and I don't know if it's going to record my using the cursor here or not, but we're going to try it. Right here, I am tracing out the fault plane. Okay, so your hanging wall is a block on the right, it's above. Your footwall is a block on the left, it's below. And we've had movement here. In this case, the hanging wall has moved up relative to the footwall. So the image on the bottom is just for practice. In a normal semester, we didn't take time for this semester. But if my cursor movement is being recorded, I'm tracing out a fault plane right here. And the more steep the angle of the fault plane, the harder it is to be able to determine which one is the hanging wall and which one is the footwall. So this one's pretty steep, but the rock on the right is the hanging wall, it is above, and the rock on the left is the footwall, it's below. And looking at the offset of the gray layers here, we can see that the hanging wall has moved up. Okay, fault trace and fault scarp. If you were in class, I asked you to write both of these down. Okay, so fault trace we've actually already introduced on a previous slide. It is the intersection between a fault plane and the ground surface. And again, this can also be referred to as a fault line. Now, not all faults are going to make their way to the surface, and that's dangerous, because if the fault doesn't reach the surface, then we may not be as likely to know that it's there. So fault scarp, if you have an active fault that slopes at an angle, and you've had an earthquake event that has produced vertical offset on the ground surface, we refer to that as a fault scarp. I believe we have some images of fault scarps coming up next. Here's a nice 3D drawing. Okay, so you can see the fault plane there, that sloping dark line. So this begs a question, right or left? Okay, which block on the right or the left, which one is the hanging wall above the fault plane? Okay, hopefully you chose the block on the right. It is indeed the hanging wall. The block on the left is the footwall. Now, we've had movement here. We've had the hanging wall drop down relative to the footwall. You can clearly see the fault trace here. That's everywhere that the fault plane intersects the ground surface. And because we now have offset, vertical offset at the ground surface, we have a fault scarp here. Here is an image of the San Andreas fault trace that we don't often see. I really like showing you guys images of offset of either Wallace Creek or Pallet Creek, but clearly this is in a farming area, and someone has carefully tilled the land here, in between. Maybe they're on crop rotation and this piece of land is being allowed to rest for a year or two. But an earthquake has occurred recently, and now you have the tilled areas here offset by at least a foot. So here's another image of the San Andreas fault trace, and I believe this is Wallace Creek again. I kind of like the black and white image. I think you might be able to see the topography a little bit better. But creeks don't normally do this, okay? So what's going on here? Well, once upon a time, when Wallace Creek was first carved, it went straight across the fault trace. But what has happened over hundreds of years is that you have had earthquakes here and there, and that is carrying the Pacific plate northwest with respect to the North American plate. So you now have Wallace Creek offset on either side of the fault trace. Here's an image of a fault scarp. Okay, so, wow, do we have offset, vertical offset of the ground surface here? Yes, indeed we do. So the people there, geologists we assume, they are standing on the hanging wall. So the angle of the fault plane here is very steep, and the more steep the angle, the more difficult it is to tell which one is a hanging wall, but the people are standing on the hanging wall, and it's dropped down by a lot. So, and the fault trace is there, it's just, you can't really see it because it's in shadow. But there's a big offset on the ground surface here, easily, oh gosh, maybe 20 feet, I would say, well over 10 feet, 20 feet. Is it possible to get that much offset in one earthquake event on a normal fault? And the answer is yes. Okay, maybe it was a couple of earthquakes that did this, and perhaps it was just one. Here's a fault scarp in Taiwan. If you were in class, we looked at this together, and I asked you guys a question. Okay, so when they built this track, maybe they did not realize that they were right on the fault trace. So clearly they've had an earthquake, and you now have a fault scarp. You got offset on the ground surface. Everything was nice and flat and level when they built this track. So enough time has passed that grass has grown over the fault scarp. Okay, so this didn't just happen yesterday. And they haven't come out yet to fix this track and level the ground and rebuild it. And I asked you guys in class why that is. And of course the answer is, why would you do that when it's just going to happen again? So now that they know that the fault trace is right there under the track, hopefully they have land on the other side of the school to put the new track on it. And then they're going to leave this one alone, and that's great, because then you can bring your science classes out there to look at the fault scarp and talk about the earthquake that produced it. Okay, so in class, I asked you guys to write down, just the first bullet here is fine. So not all earthquakes are going to be visible to us because, sorry, not all earthquakes. I meant to say not all faults are going to be visible to us because not all fault planes will intersect the ground surface. So if a fault plane does not intersect the ground surface, then we don't know it's there, and we refer to it as a blind fault because we are blind to its existence. So it may just be that it doesn't propagate to the surface. It's covered by strata, rock layers, and or sediments. And these faults can be very dangerous. And we have an example of how dangerous the faults can be. Back in January 1994, a previously unknown fault, a blind thrust fault, kind of in the region of the Hollywood Hills, anyway, it unleashed a 6.7 in the middle of the night, and it killed 60-some people. And we didn't know that fault was there prior to that because it did not have a fault trace, and it was not producing small earthquakes to let us know it was there until it was too late. Here is a drawing of a blind fault. It's not a very good drawing of a blind fault because look at the top, the ground surface there. That's clearly a fault scarp. So a geologist would see that and know that the fault was there. So this isn't the best drawing of a blind fault, but I couldn't find a lot of them. So just imagine that covered with a bunch of soil and trees and vegetation, and then you maybe wouldn't see it. Okay, so this begins an outline that we put on the board and that I filmed a few years ago for a video lesson. All right, so two basic types of faults. Number one, dip slip faults, and number two, strike slip faults. Okay, so the dip slip faults, this just means that the fault plane slips at an angle. And we're going to have three types of dip slip faults, depending upon how the hanging wall moves relative to the foot wall. Okay, in other words, does the hanging wall move up or down? By the way, the hanging wall is the only wall that moves. The foot wall does not move. Okay, only the hanging wall does, and it can move up or down. It's also going to depend on what is the angle of the fault plane. So there'll be three types of dip slip faults. And then strike slip faults are faults where the fault plane is 90 degrees vertical, straight up and down, and it's going to accommodate lateral movement, meaning sideways, side to side offset. Okay, so there are three types of dip slip faults, and you definitely want to watch the video lessons if you did not make it to class, because we have drawings on the board that better explain the fault types. All right, so normal faults, the hanging wall drops down relative to the foot wall. This, by the way, is due to extension or pulling apart, stretching. In the case of thrust and reverse faults, you're going to have the hanging wall move up for both a thrust and reverse fault. And how do you get the hanging wall to move up? That's going to require compression or squeezing. But the difference between a thrust fault and a reverse fault is going to be the angle. Okay, so a thrust fault is a low angle fault, meaning that it's relatively shallow, less than 45 degrees. And a reverse fault, you're going to have a higher angle fault or a more steep fault, equal to or greater than 45 degrees. So this is a nice 3D drawing of a normal fault. All right. So what do you have going on here? Well, notice the two big black arrows moving away from each other. This is extension or stretching, pulling apart. And what happens when you pull things apart is that the hanging wall will drop down with gravity. Okay, so it drops down relative to the foot wall. You see there are three different colors of rock layers, gray, green, and blue, that are all offset, showing you clearly that the hanging wall moved down. So where are you going to find these types of faults? Well, you're going to find them anywhere you have extension. Okay, so divergent boundaries. All right, you're going to find them along your mid-ocean ridges. You're going to find them in your rift zones like the East African Rift. You're going to find them in places where you just simply have stretching like the Basin Range Province out west. So this is a neat diagram here, and in class I did a demonstration with the blocks, and I think that particular demonstration did not make it into the video lessons. That's okay. But what you have going on here is, well, first of all, look, the big pink arrows are showing extension or stretching, pulling apart. Over on the left, you have a bunch of normal faults. And is it normal in the real world to get a bunch of faults this close together? Yes, especially in areas where you're either stretching things apart or pushing things together. Here we're stretching things apart and we're forming a bunch of normal faults over there on the left. The hanging walls for each of those faults are on the left, and the hanging walls are dropping down. Over on the right is an interesting situation where you have two dip slip faults that are angled towards each other. And what happens here is that when you stretch and pull this stuff apart, you get the block in the middle to drop down. And this forms a valley. Now, this isn't just any valley. This is not a river valley. This is a valley that's been formed due to stretching. Okay, so those terms, Horst and Graben, are German terms. Just know that there's more than one way to make a valley. In this image here, this is a road cut, of course, and there are several faults on this diagram, and honestly, it's there's probably a little more going on here than we need to worry about. This might be a great image for a structural geology class, but I will call your attention to the fault over on the far left, and you can clearly see the fault plane there. Can you tell which block is the hanging wall? Is it on the right or is it on the left? Hopefully you can see that it's on the right, and looking at the offset of the darker brown layers, you see that the hanging wall is dropped down. So this is a normal fault. Here we can clearly see a couple different faults So make sure that you're able to look at these and trace out the fault plane. Okay, so let's go to that fault that's in the middle of the picture there. Which one is a hanging wall, right or left? Hopefully you chose the one on the left. And how has it moved? It's moved down. This is in a quarry. So abandoned quarries are popular places for people to go and hang out and even swim. Just know this, quarries can be dangerous, okay? You always want to be real careful. And sometimes people that thought they were okay at swimming drown in quarries because that water can just drop off to deep levels faster than you expect it. So be careful around quarries. But quarries are a great place to look at the rock, that's for sure. So in the middle of this image here, there are a couple of normal faults. So you see the fault plane dipping down there to the bottom right. And then in each of these faults, notice the faults are very close to each other. In each of these faults, the hanging wall's on the right. And in each of these faults, you've had that hanging wall drop down. So these are two normal faults exposed in a quarry. Okay, so a little bit more about our thrust and reverse faults. Again, both of these are going to result from compression or squeezing. So in our video lesson where we use the block diagrams, I squeeze the blocks together and that makes the hanging wall move up relative to the footwall. And of course, the only difference between a thrust and reverse fault is going to be the angle of the fault plane. So a couple of drawings here of our thrust faults where again you have a shallow angle, less than 45 degrees. Let's look at the one on the right first. So right or left, which block is the hanging wall? This should hopefully be pretty obvious that the one on the left is the hanging wall. It's clearly above the fault plane. And it's easier to see that when the fault plane is rather shallow. And of course, you've got the big arrows moving towards each other. You're squeezing, compressing. The hanging wall slides up relative to footwall. On the left, we have a 3D drawing of a thrust fault. And this is kind of nice because it's showing that mountains are getting produced here as a result of the squeezing. So mountains and thrust and reverse faults are going to form in this type of setting. The big white arrows are moving together, squeezing. And in this case, you've moved the hanging wall, the block on the left, up and over the footwall by a large distance. And how do we know that? Because, well, I want you to look at the blue layer on the left and then look at the block on the right, the footwall, and see, do you see that blue layer at all? There's a little sliver of it there at the end. Just giving you an idea that in the real world, sometimes the hanging wall gets pushed up over the footwall by several kilometers. So it's a long process involving squeezing and many earthquakes to achieve that kind of offset. So again, how is the reverse fault different from the thrust fault? It's just the angle. That's the only difference. So the hanging wall will move up relative to the footwall, just like the thrust fault. This will be a result of compression or squeezing, but the angle of the fault plane is going to be steep. It'll be greater than or equal to 45 degrees. Here we have a couple of drawings of reverse faults. So the one on the right, the top right, I have to admit that that angle is pretty close to 45 degrees, but it's close enough to 45. We'll go ahead and call this a reverse fault. Hanging wall's moved up because you have squeezed. Okay, so the one on the bottom left is a good one to practice because this one has not been labeled. So the first thing we're going to do is try to determine which block is the hanging wall, on the right or on the left. Okay, hopefully you can see that the one on the left is above, so that's the hanging wall. And how has it moved? It has moved up. And that is a result of compression or squeezing. So we can imagine big arrows on either side pointing towards each other. We'll try this again. I clicked too quickly. Maybe it's not going to give us the arrows. Anyway, yeah, hanging wall clearly has moved up here relative to footwall. Okay, so a little more about our strike slip faults. I'm going to want you to know an example of a strike slip fault. Well, that's easy. The mighty San Andreas is the best example and the most famous example in all the world, I think. So your fault plane again is vertical, straight up and down, 90 degrees. We've got drawings on the board that you'll find in the video lessons. And what's going to happen here is that the rock on either side is going to slide past each other. So it's lateral offset, side to side offset. You're really not expecting vertical offset with your strike slip faults. So here are a couple of decent 3D drawings of your strike slip faults. So look at the fault planes first of all. Notice they are straight up and down 90 degrees, and that your offset is side to side. And that offset can either be right lateral or left lateral. And we did a very quick demonstration of right lateral versus left lateral in class. And that notion of whether or not a strike slip fault is right lateral or left lateral is going to be extra credit on your final exam. This is a better drawing for right lateral versus left lateral anyway. This is another image of your strike slip fault. This is what they look like from the ground surface. Okay, so here we're not looking at a road cut. We're not imagining looking down into the shallow subsurface. We're just looking at it from the ground level. So, and look at the two images on the right where you've had movement. The one on the top labeled left lateral. What's going on here is if you stand at the fault trace with your toes touching the fault trace and you look across to the other side, notice that the road has moved to your left. If we look at the images on the bottom right here that are labeled right lateral, same thing. If we imagine standing right there at the fault trace with our toes touching the fault trace, looking across to the other side, how has the road moved? It has moved to our right. Here's another image of the mighty San Andreas. All right, you guys tell me. I'll take a second. Okay, so hopefully you can see that fault trace running from right to left across the bottom half of our image here, and then you see the offset of Wallace Creek. Okay, which one is it? Is it right lateral or left lateral? Hopefully you picked right lateral. Okay, last time we'll practice with right lateral and left lateral. Do we see the fault trace? Okay, so it's kind of moving kind of up and down here, kind of northeast to southwest in this image. And then look at the offset of the light colored layers there. So is this right lateral or left lateral? Imagine standing with your toes at the fault trace looking across the other side. So I'm hoping you chose left lateral. Okay, so now when we trace this out, it might make it a little bit easier to see. This is left lateral. And indeed, this is left lateral, so we can put our arrows on either side of the fault trace there, showing the offset. We do this on geologic maps as well. Okay, so just for fun, I wish I could say that I was clever enough to come up with this, but no, this is not my cat, and I didn't do this. A friend of mine found this online and sent it to me. The scratch post is the foot wall. The cat is the hanging wall. And of course, this is a very lazy cat that is not going to scratch on the scratch post, but just wants to take a nap on it. So they had to scoot it up against a piece of furniture there. It looks like a desk. So if you take the foot wall and you move it outwards, in other words, you're making extension, what's going to happen to the cat, the hanging wall? It's going to drop down. Okay, this information here on this slide is not on your exam. And we didn't take time for it in class because, well, it's alternate hybrid now. But in the real world, there are more interesting faults than just what we have discovered, okay? So there are times that you can have both strike slip movement and vertical movement at the same time, all right? So oblique transtension is where you have strike slip lateral side to side movement, but also extension with the hanging wall dropping down. And then oblique transpression occurs when you have both strike slip lateral movement, but also some squeezing compression that makes the hanging wall move up. So in the real world, you can have a combination of both lateral offset and vertical offset together. So these drawings here in 3D, okay, I could not make these drawings, I'll tell you that now. Jobs for artists. Anyway, so the one on the top left shows oblique transpression. You've got your strike slip motion, but also your hanging wall moving up. and then the one on the right shows oblique transtension. So here you have your strike slip motion, but also the hanging wall moving down. Just know that in the real world, it's always going to be more interesting and more complicated than how we might present things in a typical, introductory class. All right, so fault types and plate boundaries. In our notes in class, we kind of put all this together in a big outline. We did it all in one day in class, one class period. This is listed in your video lessons, so we'll move through this quickly. Okay, so spreading centers is in mid-ocean ridges, rift zones, and anywhere you have stretching, crustal thinning, extension, you're going to get normal faults. Your convergent plate boundaries that are associated with compression, okay, so this is going to be all three convergent boundaries, continent to continent collision, and then both ocean to continent and ocean to ocean subduction. It's in these plate boundaries you're going to find thrust and reverse faults. And of course, where are you going to find strike slip faults? Where you have that lateral offset, where you're going to find that at your transform boundaries. So yeah, the San Andreas Fault is our best example, but another good example is the North Anatolian Fault in Turkey, which is also a right lateral strike slip fault. But that is not the fault that produced the earthquake 2 days ago in Turkey. But it produced a really devastating earthquake back in 1999 that killed thousands of people. Both the San Andreas Fault and the North Anatolian Fault, they are not only strike slip faults, but they're true transform boundaries. They're both right lateral. Okay, you don't need to write any of this down here, and we did not take time for this in class, but we'll briefly discuss it here. One of the scary things about your strike slip faults is that every earthquake they produce is going to have a shallow focus. And so they're very dangerous. Actually, I think I did write that on the board for our board notes this time. All right, your thrust and reverse faults are capable of producing major earthquakes. And in particular, your subduction zone areas, ocean to continent and ocean to ocean, tend to produce the largest earthquakes, especially if that earthquake occurs right there at the plate boundary, right at the plate interface. The good thing about your subduction zone earthquakes is that a good number of those earthquakes tend to have a deeper focus. And that's good, because the deeper the earthquake occurs, the less hazardous they are to us at the surface. And our strike slip faults, like the San Andreas, I personally don't think the San Andreas is capable of producing a 9.0 to a 9.5. I hope I'm correct about that. And even the Great San Fran quake in 1906 was only a 7.9. But even if you only get up into, say, the high 7s or the low 8s on strike slip fault, they're still very dangerous because the focus of that earthquake will always be quite shallow. Okay, a couple other things you do not need to write down. Things that we might discuss in class if it's a normal semesters. So normal faults are not often producing super high magnitude earthquakes. Not often, but that does not mean that it never occurs, okay? And a very bad exception happened way back in 1891 in Japan, and this was a normal fault, and it was an 8.0. That's really big for a normal fault. And there was 16 feet of offset in one earthquake event, and it killed almost 7,000 people. Think about 1891. There weren't nearly as many people on the planet back then in any country, including Japan, and yet it still killed 7,000 people. Okay, so some interesting things here about the San Andreas Fault that are not on your exam. It is 800 miles long, stretching from the Salton Sea, which is down there in Southern California. So basically the East Pacific Rise, remember that it has created the Gulf of California, and then when it hits land there around the Salton Sea, it transitions into the San Andreas Fault. And that San Andreas Fault will run all the way up to north of San Francisco, where it's going to run offshore to the west and transition into the Mendocino fracture zone. So, some interesting things here about that ancient Farallon plate. So about 300 million years ago, you didn't have the San Andreas Fault yet. San Andreas is really young, like maybe 28 million years of age at most. 300 million years ago, you had the Farallon plate subducting beneath the North American plate from Mexico all the way to Alaska. The angle of subduction was about 50 degrees, which is relatively steep, but it flattened with time because we had a mantle plume beneath the Farallon plate that kind of buoyed it up. So, the subducting angle now of the Farallon plate is actually pretty shallow. And that's part of why the Rocky Mountains or just in general, why we have mountains as far inland as we do. And the Rockies are relatively young, honestly. They're just not very old. I want to say less than 50 million years for the Rocky Mountains, maybe more like 34 million years. Anyway, more interesting things here about the San Andreas Fault, not in your exam. Don't have to write them down. About 28 million years ago, the Pacific Plate first made contact with the North American Plate. Okay, at that point, the Farallon Plate was, pretty much completely underneath the North American Plate, although there are some remnants of the ancient Farallon Plate both in the Northern Hemisphere and the Southern Hemisphere. The Juan de Fuca Plate, the Gorda Plate, the Nazca Plate. Anyway, so when the Pacific Farallon Ridge, mid-ocean ridge that was separating those two oceanic plates, made contact with North America, well, then things changed. So this created two triple junctions in Southern California, one at the intersection of the North American, Juan de Fuca, and Pacific plates, and the other at the intersection of the North American, Pacific, and Cocos plates. As the North American plate moved west, the triple junctions migrated north and south, respectively, and we ended up transitioning from a big subduction zone, all on the west coast, to our strike-slip fault transform boundary, the San Andreas Fault. So here's a nice drawing. It's very simplified, but that's okay. Here's a drawing of the San Andreas Fault system. And we really should think of it as a fault system, not just a discrete fault. Is there the San Andreas Fault proper? Yes, but the fault zone, fault system, is complex and stretches for many, many kilometers in an east-west direction here, in width, we might say. And there's a bunch of smaller faults that are part of the plate boundary here, like the Hayward Fault and the Calaveras Fault. The Calaveras Fault, by the way, is where we get fault creep. The Hayward Fault is really quite dangerous, and probably the next large quake we have in the general San Francisco area is quite likely going to be due to the Hayward Fault, not the San Andreas. Notice in Southern California you have the Garlock Fault, which is perpendicular to the San Andreas Fault system. That's a very dangerous place, and that's a place where you have oblique transpression. So not only do you have your strike-slip movement, but you also have compression, and that has helped to build some of those mountains there, the San Gabriels, I believe. So on this slide and the next, it's something from, well, either an older textbook or our more recent textbook, just mentioning that earthquakes tend to occur at plate boundaries. Sometimes we do get intraplate quakes, but probably 95% of earthquakes on this planet not only are at plate boundaries, but are in a few narrow zones, like the Pacific Rim, the Circum-Pacific Belt, and the Alpine Himalayan Belt. And then, of course, transform boundaries and strike-slip faults are going to make up some of that 95%. So here is a decent drawing showing where most of our earthquakes are taking place. So you've got plenty of them there on the Pacific Rim. You've got them in all the mid-ocean ridges of the world. You have them mainly at your major plate boundaries. Of course, you have them all through the Alps and the Himalayas because you have compression there. But here and there, you do have them kind of scattered out throughout a plate in the interior of the plate. And I'll call your attention to North America. And west of the Appalachian Mountains, there's a red dot, and that is where the New Madrid fault is, the real foot rift, failed rift that we talked about back with plate tectonics. So it's not a plate boundary, but millions of years ago, it attempted to become a plate boundary. And it was not successful. You did not split the North American plate. But it created faults that never heal, and we do have movement on those faults from time to time. Okay, paleoseismology is one of my favorite topics, and if you want to, you can pause and read through this, but paleoseismology, not on your exam, by the way, this involves looking for earthquakes that happened in the past, before you had people living there that had a written language, you know, to write these down and make scientific note of it. So this usually involves digging trenches across fault traces and looking for offset in layers, maybe looking for sand blows, and of course taking some samples that you might be able to use for radiometric dating to get some idea of when these past events occurred. Okay, now we're going to get into the seismic waves. So we had a brief outline on the board this past week. No, it did not make it into a video lesson. That's okay, it's here in the narrated PowerPoint. So you might start yourself an outline. You need to write these down. Okay, so two main types of seismic waves. You got the body waves and the surface waves. We will see on upcoming slides that we're going to have two types of body waves and we're going to have two types of surface waves. So your body waves are seismic waves that pass through the interior of the Earth. We have two types. We have the P waves and the S waves. We've learned a little bit about these waves already back when we talked about plate tectonics. Remember that the P waves travel through solids and liquids, and the S waves only travel through solids. Now the surface waves, we haven't talked about yet. These are your seismic waves that propagate along the surface. And they're going to form whenever your body waves hit the surface and still have energy. So they propagate along the surface until that energy is dissipated. So the surface waves are going to move slower than the body waves, but the surface waves are going to be more damaging than the body waves. Okay, so our first type of body wave is a P wave. We think of them as compressional waves, and what that means is that the rock material is going to squeeze together and pull apart, compress and dilate, parallel to the direction of wave travel. So we did model this in class with a slinky, and there's going to be a static drawing of a slinky to show this. All you really need to know about the P waves is they're one type of body wave, and they travel through solids and liquids. And they happen to be the fastest, by the way. They arrive first at seismometer. Earthquake sound, not in your exam, but an interesting topic when we've got a second. So P waves, being that they are compression waves, they travel kind of like sound waves. Okay, so when a P wave emerges from the subsurface, you know, most of that energy will propagate along the surface as surface waves, but a fraction of that energy will get transmitted up into the air as a sound wave. We just don't always hear it, okay? So if the frequency is greater than 15 cycles per second, then humans and animals will hear it. Okay, so this is why sometimes when people live through a large earthquake, they might talk about a sound. And it's not the sound of the buildings rattling or the buildings falling down or anything like that. It's a different sound. But they don't always talk about hearing a sound because it depends on what is the frequency of those P waves when they bounce into the air. Okay, our second type of body wave are called the S waves. And they're called S waves because they're secondary waves, meaning that they arrive second at the seismometer. But we think of them as shear waves, meaning that we're describing how they move. Okay, so what happens here is that the particles of rock are going to move back and forth perpendicular to the direction of wave travel. Okay, so kind of like a snake might move across the desert. And we can show this with a slinky as well. It's probably better to use a rope to show this. And we have a static drawing of a rope coming up that'll show you what an S wave looks like, how it travels. And the thing with the S waves traveling as a shear motion, the reason they won't go through the liquid outer core is because liquids do not have shear strength. And of course, this is how we know that the outer core is liquid. No, we never drilled there. We'll never be able to. That's okay. Here's a nice static drawing trying to show how a P wave moves, okay? So in the drawing on top, imagine that that's a big block of granite, okay? And then the rectangles there are just individual feldspar crystals, say, in the granite. They kind of might have that rectangle shape. So the drawing on the bottom is showing what's happening to individual rock particles as the wave energy moves through the rock. So the direction of movement is to the right. And then you're going to see there that these particles are squeezed together and then pulled apart, squeezed together and then pulled apart, parallel to the direction of wave travel. This is what we mean when we say that P waves are compressional waves. This is what we did in class with a slinky. I kind of like the static drawing. So you just hold the slinky still and you just push at one end, and what you're going to see is you're going to see what looks like something dark kind of traveling through it. And where it looks dark is where the pieces of metal are compressing together. But they'll compress together and then squeeze apart parallel to the direction of wave travel. So this is a nice static drawing trying to show how the S waves travel. Okay, so this is in the subsurface and our focus is to the left where the earthquake began. And what's happening to our individual rock particles is that they are moving perpendicular to the direction of wave travel. So you might think of them as moving up and down. So here are some animations. For the P wave, it's best to look at the yellow box and not the dot. But so the yellow box is showing you pretty well what's happening to individual rock particles as the compression wave moves through. The S wave there in the middle, I think it's better to look at the green rectangle than the red dot. And you see there that the rock particles are moving perpendicular to the direction of wave travel, a shear type of motion. And then on the bottom, that's surface wave. And which one? That is the Rayleigh wave, known as ground roll. So we did not do this one in class only because we don't have a rope. We could easily do it, but I don't have a rope and I'm not going to go buy one. If my department buys one, fine. So you could simply tie the rope to a door handle or have somebody hold the other end and then just move your wrist up and down one time. That's all it takes. And you're going to see that the individual fibers of the rope are moving up and down or perpendicular to the direction of wave travel, and you can see that S shape, we might refer to it, moving across the rope. Okay, so these images here, when we have more time in class, we do look at them. I know they're a little fuzzy. The document camera was not doing well that day, but it's okay. So on the top drawing, that's your P wave. So your, I don't know, we'll say it's a 4.0 earthquake has just occurred. It's a pretty shallow focus. And the first thing that you're going to feel if you're right there at the epicenter is the P wave. Okay, so the P wave hits first. It's going to feel like an up and down jolt. The S wave will come second. It's a little slower. And when it hits, it's going to feel like a side-to-side jolt. Okay, what about our surface waves? Okay, so I had everybody in class write, well, they wrote down the outline we had on the board. You're going to need to know your body waves and your surface waves, your two types of body waves and your two types of surface waves, but you also need to write down this first bullet here. So the surface waves are an issue, okay, because they cause the most shaking and the most damage during an earthquake, all right? That's because they have the greatest amplitude of ground shaking. So surface waves are worse than body waves. And the surface waves are the greatest challenge to civil engineers, especially the love waves. That is an extra credit question. But we'll begin with the Rayleigh waves, and these are named for scientists who worked on them and studied them. That's Rayleigh, not Raleigh. Rayleigh waves are surface waves that cause the ground to ripple up and down vertically, also known as ground roll. You do not need to know that the Rayleigh waves are caused by the P and S waves together. The Rayleigh waves are the slowest, and that's just kind of an interesting thing. But people that live through large earthquakes, and let's say they're somewhere safe, like outside, and there's nothing really you can do other than just, kind of hold on tight and watch it happen and hope everybody's okay, and maybe get out your cell phone and film. But the people that live through the big earthquakes and are outside, they will talk about visible waves on the ground surface. It's a pretty big quake when you can very easily see those Rayleigh waves. Rayleigh waves, they can knock trains over. They can knock cows over. This is a nice static drawing showing what's happening to the individual rock particles as the surface wave moves on through. And the particles are basically rolling up and down. It's very similar to what happens to, say, an object caught in the waves in the ocean near the coast. Okay, our second type of surface wave is called the love wave. Okay, and these are surface waves that cause the ground to ripple back and forth in a snake-like movement. And it's just the S waves alone that are causing the love waves. What I want you to know about the love waves, other than they are one of the two types of surface waves, is that the love waves are the greatest challenge for civil engineers, meaning that they can build, design, retrofit buildings, bridges, overpasses. They can design them pretty well to withstand the up and down motion of the Rayleigh waves. But some of our large quakes in California in recent decades were quite surprising to the civil engineers, and they had not expected the amount of side-to-side offset that we would have in an earthquake that was just in the high sixes. So here are some static drawings of what the Rayleigh waves, of course the drawings are exaggerated. The waves aren't going to be that big, but kind of give you an idea of what's happening at the ground surface as your Rayleigh wave comes through. That's your top drawing. And as your love wave comes through, which is your bottom drawing. And then here are some even older versions of the same thing that we saw on the last slide, just trying to give you an idea of the motion that you might experience at the ground surface with the love wave, which is on the top drawing this time, and the Rayleigh wave on the bottom drawing. Okay, shallow versus deep earthquakes. I believe I wrote this first bullet on the board in class the other day. You definitely need bullets 1 and 3 here. Okay, so shallow earthquakes. Here's the thing. Does the magnitude of the earthquake matter? Well, of course it does. A larger magnitude is more energy, more ground shaking, more damage, death, and destruction. Does the location matter? Well, of course it does. The epicenter matters. If your epicenter is out in the desert where nobody lives, that's great. But if your epicenter is close to downtown Los Angeles, that's terrible. But the depth of the earthquake also matters, okay, because shallow focus earthquakes cause more shaking and more damage than deep focus earthquakes. Okay, so depth does play a part. And again, I think we mentioned this earlier in this presentation, one of the scary things about the strike slip faults is that every earthquake they produce is going to have a shallow focus. No such thing as a deep focus earthquake on a strike slip fault. So your large quakes along strike slip faults, even if they're only in the high sixes, can cause major damage. Stick slip behavior. Okay, so for people that are going to be coming to class this week, this is where we will begin as we finish up our unit here on faults and earthquakes. So stick slip behavior. Okay, so here's the thing. Faults are not smooth. Okay, they've got bumps and bends. There's a lot of friction on the fault because in a lot of cases you have squeezing. Even if it's extension, there's still friction on the fault plane. So this means that you get a lot of stress to accumulate along your faults in between earthquakes. Okay, why? Because the friction keeps the faults from moving smoothly. So you go longer periods of time in between earthquakes because of the friction. But the problem there is that the longer time you go in between earthquakes, the larger that next earthquake is going to be. So this is the stick part of stick-slip behavior. So what about the slip part of stick-slip behavior? Okay, so as the stress on the fault plane overcomes rock strength, then you're going to have movement. You're going to have slip, offset, and rupture. Okay, so it's true that the rupture, breaking the rocks, is going to release some energy, but a large portion of that energy that's going to travel as seismic waves is actually released as undeformed rock elastically springs back into, as deformed rock elastically springs back into undeformed shape. So if you go to YouTube and you type in stick slip behavior, you are going to find some decent videos out there where somebody is, there's either animations for showing stick slip behavior, or somebody is able to model it in a lab or a classroom. So basically what this means is that, let's say it's a strike slip fault, and the rock or the plate on one side is trying to move relative to the rock on the other side. So what's going to happen there is that in the decades of stress buildup in the stick part of this scenario, the rock layers are actually going to bend. They're going to deform. Okay, and this is happening because you have a bunch of small fractures forming. You cannot change the shape of something solid in the brittle realm without creating fractures. But you're going to have these rocks bending on either side of the fault plane. And this is storing up elastic energy, okay, perhaps for decades. And then eventually the stresses overcome rock strength, and you have your earthquake, and you have your offset. And what's going to happen very instantaneously when that earthquake occurs is that the rock layers on either side of the fault, they were deformed, but they're going to elastically spring back into an undeformed shape. And this releases a lot of energy. Okay, and that's where the majority of your energy is coming from that produces the body waves, P waves and S waves. Okay, so after the earthquake has happened, we might say that the stress along that particular fault plane, or that section of the fault plane, has been released. But you know what? It'll just build up again over the coming decades, getting ready for the next earthquake. So, in class, in a normal semester, and maybe this coming week, if there's time, we will look at a couple of animations from the IRIS website. That is IRIS, and it's Integrated Research Institutes for Seismology, to make sure you get to the right IRIS site. And they have a lot of animations dealing with earthquake behavior. Okay, so but even this static drawing here will do for now. It looks like something from a Physics 2 lab, sure, or maybe a Physics 1 lab. Well, I don't know, some physics lab. Okay, so what we're going to imagine here is that we're going to set up this experiment. So we go out and find an old wooden table at a flea market. And this table is 100 years old, and it's got all kinds of chips in it, and it's got splinters, and nobody's refinished it in many decades. It's not smooth. And then we go out to Michael's Crafts, and we buy a big wooden block, and it hasn't been sanded yet, so it's also not smooth. So the block is M, and the old wooden table is X. And then we go to our friend, say Dr. Brandon perhaps, in physics, and we ask if we can borrow a spring, a metal spring. And that's what V is, it's a metal spring. Okay, and of course where K is, that's where you've got, the part of a spring that makes it a spring. So what we're going to do is attach this metal spring to the wooden block. And then there at the end where the arrow is, we're going to grab the end of that spring and we're going to pull gently. Okay, just gently, but consistently. So this big heavy block that is not smooth, sitting on top of a table that's not smooth, is it going to move right away when we start pulling? Well, no, it's not going to. Because what's going to happen first? Well, that part of the spring that is, the spring part is going to stretch. Okay, that's the first thing that's going to happen. And that's going to represent decades of stress buildup on the fault planes. And eventually, if we keep on pulling, we're eventually going to get that big, heavy wooden block to move. But when it does, it is not going to be smooth. It is going to jump. It is going to lurch. It's going to be a violent motion. And that's a really great analogy to stick-slip behavior. You can also, if you want to, copy and paste these two websites I have here, and that should take you, well, you'll notice the one on the bottom is from the Iris website for sure. Anyway, it'll take you to some really useful animations. Okay, so related to stick-slip behavior is this notion of elastic rebound. And really elastic rebound, we've been discussing it in the past couple of slides. Okay, so kind of putting it all together, stick-slip behavior says that fault planes are not smooth, just like our block on the wooden table. It's not going to easily move because of friction. But eventually, the stresses on the fault plane, or us pulling on that elastic spring, are eventually going to overcome the strength of the rock, and then you will have your movement. Okay, so that's the stick-slip part of this. And then the elastic rebound theory has to do with the rock deformation. So we say that stick-slip behavior and elastic rebound theory are working together, kind of like Batman and Robin, or peanut butter and jelly. All right, so again, you're going to have friction on the fault plane because they're not smooth, leading to stress buildup. This is going to allow those tiny fractures in the rock on either side of the fault plane. So that rock's going to deform and bend. And then again, instantaneously, when your earthquake is happening, you're going to release the stresses on those rocks, and they're going to elastically snap back into an undeformed shape. And that's releasing your energy, seismic waves. So when the earthquake is over, here's what you're going to find. The rock layers are not bent anymore, but they are now offset and they are now broken. So I really like this image here. I don't know that I'll have time to show this in class, but we'll talk about it here. A good analogy for this is to imagine that your grandparents, many decades ago, bought land in California, and they're going to have a small farm, horses and maybe a couple cows, and they don't know that they bought land right on the fault trace, and they put a fence up. So over the decades of your parents growing up and you being a young person to go and visit them, you've never seen that fence straight because you came along decades later, and you've always wondered about that crooked fence on your grandparents' property. And you ask your granddad, why did you build the fence crooked? Were you drinking beer that day? And your granddad says, I can't drink beer in front of your grandmother. I built that fence straight across, and it is now bent because it's on the San Andreas fault trace. So the wooden fence is kind of mimicking what the rock layers, how they're behaving in the subsurface below. Okay, so then in the bottom left, that is the instant that the earthquake happens. You've got offset, you've got breakage, you're releasing energy and shaking the ground. And then on the right, that's what it looks like when you come out to visit on your spring break to help your grandfather repair the fence. So the fence is no longer bent. It's no longer, in kind of a wavy shape, but it is broken and it is offset. And again, the behavior of the fence at the surface is a great analogy to what's happening to the rock layers below on either side of the fault plane. Here's another good static drawing. So over on the right, we could do this in class. We don't, just because I don't like to break pencils. What I do is I hold a pencil up to my ear and I start bending it, and I ask the class, If this pencil were brand new and I'm bending it for the first time and I put it by my ear, what I'm going to hear? And somebody will answer, you're going to hear little pops because you're making little fractures, little breaks in that pencil to make it bend a little bit. So we see this in the set of drawings on the right. You take your stick or pencil, whatever you're going to use, maybe a yardstick, and you start to apply your stresses, and you're able to bend it. And it hasn't broken yet, but if you keep on bending and you keep on applying those stresses, you will overcome the strength of that pencil, and then you will break it. And if you have a sophisticated video camera that's going to, capture all this motion, and you then could replay it in slow motion, you would see that third image down there. You would see that's your elastic rebound. At the moment you break that pencil and the earthquake occurs, the bent pencil halves on either side are going to elastically snap back into an unbent shape. And that's what you see on the bottom right. Of course, what they should have done is push one of their hands a little bit higher so that you could notice the offset there of the pencil on either side. And here's just a drawing of what that fence that your grandfather built, looks like. Way back when they built it, and then for many, many decades, you have that fence kind of, looking more like an S pattern, as in it's being deformed on either side, and then what it looks like after the earthquake and after it has broken and been offset. Okay, you can pause here and read through this if you want to. Again, on this slide, you can pause and read through this if you want. We normally skip this in class. Okay, locating an earthquake. This is not on your exam. If we ever mention it in class, it's very brief, so we won't spend much time on it. Basically, it's really easy to do, and you just need 3 seismometers. You need the printout or record from 3 different seismometers to find where the epicenter was. And your P waves always arrive first, and the S wave arrives second, and then your surface waves are later. But you're basically going to look at the lag time, meaning how much time passed between the arrival of your first P wave and your first S wave. You look at that information from 3 different seismometers, and then scientists have constructed a travel time graph, and you can use this to find the distance to the epicenter. So here's an image of an old-fashioned seismometer where you have literally a rotating drum of paper, and then you have this pen on a stylus, and if there's nothing going on, then it'll look quite flat, or maybe there's a little bit of movement because it's in a farmer's field and there's horses galloping above. When your earthquake occurs, you can really see it, and that's when you start to get the movement back and forth on your seismograph. Here's an up-close view of the old-school seismometer. Okay, this image is important, and I hope I have time to do this in class this week. I don't know that we will. But if you start from the left and move to the right, what you're going to see is your first arrival of the P wave. And then a little background noise, then so first arrival of your P wave, and then a little bit of shaking from the energy from that P wave, and then the first arrival of the S wave, and some shaking from that. Now notice the surface waves, okay? So your distance from peak to trough is represents your amplitude of ground shaking. So between P waves, S waves, and surface waves, which of these waves has the largest amplitude of ground shaking? And the answer is surface waves. So here's what one of those travel time graphs looks like. And some semesters in lab, if we have time, we might actually do something with locating the epicenter of an earthquake. And then when you know the distance, you can then use a map and a map scale and a compass, not the kind of compass that you navigate with while hiking, but the kind that has the pointy end and then the little golf pencil on one end. And then you draw a circle with a radius equal to the distance, so 3 circles from the center where the seismometer reading is located. And when your 3 circles intersect, where they intersect, that's going to be your epicenter. So this is what we mean by that. Okay, so this is your old school way to locates the epicenter of an earthquake. So here we used information from seismometers that were in Paris, Nagpur, which is in India, and Darwin, which is in Australia. Okay, so rock response to stress. You may pause this and read through this if you would like to. This is fun information, but it's beyond the scope of this class. If I ever get to teach structural geology, those students will consider brittle versus ductile or plastic deformation. So here's another image of the San Andreas Fault. Now in this case, they're just showing the San Andreas Fault proper and not all those other faults that are part of the system. And that's okay, because what I want you to look at is the bend that you have there between Soda Lake Road and Fraser Park. Right there, we might say that the fault is crooked as a dog's hind legs. Okay, and that's bad, because the Pacific Plate, which is on the left, is moving northwest. And that means that where you have that bend, you have oblique transpression, and you have not only the strike-slip movement along this fault, but you also have compression. And that's why you have some mountains there that are running perpendicular to the fault. And this slide here, we're going to skip it. You can pause and read through this if you want to. There's nothing wrong with that. So it mentions the oblique transtension that we just spoke of, the oblique transpression that we just spoke of down there between Soda Lake Road and Fraser Park. But this also mentions that further north, like around Half Moon Bay, which is up in the San Fran area, you're going to have the opposite, oblique transtension. But this is beyond the scope of this class, not on your exam. This is an example of a sag pond, and this is something that can result from that oblique transtension. So again, this is not on your exam, but it's just interesting. So here, like you might see in some parts of the more northern portion of the San Andreas Fault, you have not only strike-slip motion, but you have pulling apart. So you end up with these little valleys, and they can fill up with water. So we call them sag ponds. And the geologist knows when they see these sag ponds that that is evidence for oblique transtension. And here's that map again of the San Andreas Fault system, and I'm just going to highlight again the Garlock Fault there that is perpendicular to the San Andreas, and what you have there is oblique transpression. So if we were in class, I would ask you to write down bullets 2 and 3. So seismic waves, the PNS waves, the body waves, are first formed at the focus, and then they travel outwards in all 360 degrees, and when they hit the surface, they're going to propagate along the surface in the form of surface waves. But you'll notice that when they have large earthquakes on the West Coast, we don't feel it here. We hear about it, but we don't feel it. And that's because of that second bullet there. Okay, so friction, while friction on a fault plane is bad because that leads to that stick-slip behavior and stress buildup, the friction is good in the fact that it's absorbing energy as the seismic waves travel through the rock layers. So a 6.9 in California today, we are not going to feel it here in North Carolina, because the energy associated with seismic waves is going to lessen or dissipate as they travel away from the focus. So of course, as we expect, greater damage closer to the epicenter. Here again is a nice 3D drawing of a sloping fault plane, an earthquake, and the epicenter, and then you see there the wave fronts as the PNS waves are leaving the focus. Brittle versus ductile deformation. We're going to skip this. We normally do. This is beyond the scope of this class. If we ever got to have a structural geology class, we would discuss this in that class. So if you want to pause here and read this, you can. You don't have to. It's not on your exam, but it is really interesting. Basically, we're saying that faults in the continental crust will experience strictly brittle deformation in the upper 12 to 16 kilometer depths. And below that, you get more of a ductile deformation. Now, that being said, even though it's ductile deformation, we still get earthquake focuses, especially along our subduction zones at depths well below 12 to 16 kilometers. You can also skip this slide, or if you want to, you can pause and take a look at this. The neat thing about ductile deformation is that it leads to bending and folding of rock layers without breakage. So this is a zoomed in image of something we would refer to as a myelinite gneiss. You might remember talking about gneiss when we talked about our metamorphic rocks. It's a metamorphosed granite. But when you have the mafic minerals all together and the felsic minerals all together, that tells you that rock has been metamorphosed. But when you have those, that compositional layering, when you have those layers deformed and all convoluted like that, you know that this is a result of ductile deformation. But again, that's not on your exam. Fault creep. I would write down the third bullet here. Okay, so we spent some time discussing stick slip behavior and elastic rebound behavior, and the fact that you know, earthquakes, the faults generally are not smooth, and you have stress buildup for decades in between large quakes, and then you have a larger quake and a lot of movement and offset and ground shaking. And that's true of the majority of faults on this planet. But in some cases, some faults or some parts of faults might actually move smoothly without large earthquakes. We call this fault creep. So I will ask you on the exam, which town in California experiences fault creep along that section of the San Andreas Fault? And the answer is Hollister, California. So they are actually on the Calaveras Fault, which is a subsidiary fault to the San Andreas, but it's part of the fault system. It's part of the plate boundary there. And when I first learned about fault creep, I was told by the professor teaching that class that we didn't really know why fault creep occurs in some places. Well, I have read a couple of scientific papers since then where they've been studying this, and so we think we have it figured out. So one thing is, you know, maybe you have weaker rocks in that area and they're all fractured up, so they're not going to store up so many stresses, so the earthquakes will occur more often and therefore be lower magnitude. But another reason is a metamorphic mineral called serpentine, and it's greenish color generally, and it's a fibrous asbestos form mineral. It's very soft, and if you have that mineral there in your fault plane, that basically lubricates the fault plane and will allow for the movement to be to allow for movement to occur more easily. So again, in Hollister, California, your earthquakes are going to be more often, but that's okay because they're smaller magnitude and it's just not a big deal. So that's fault creep, and it happens in Hollister. So this is an image from Hollister, and in this case, the offset of the fence in this person's yard, that didn't necessarily occur in just one earthquake event. So fault creep, you've got this sort of creeping movement on the fault just a little bit at a time. This is one of my favorite images here from Hollister, California. So the house there on the left, so you'll notice the yard is raised up. Well, and it might just simply be that they put in that wall as a retaining wall after buying that piece of property. But the important thing is that the house and the yard and that wall and the sidewalk, they're all going right across the fault trace there, the Calaveras Fault. And you see the fault trace there in the white dotted line. Okay, and how do we know that the fault trace is there? Because of fault creep. So they did not build that retaining wall crooked like that. Okay, that happened after it was built. And it's this slow movement, little bit at a time, along the Calaveras Fault that we call fault. So this is a winery in Hollister, California, So you'll notice clearly this is not a natural stream. This is some kind of irrigation project. It's made of concrete. It's man-made. Anyway, that image on the left there, they've had some slow offset there of their irrigation structure. Okay, this is just kind of a neat image here, especially the one on the left, because it gives you the names of the faults. So they're kind of zooming in on the San Francisco, Oakland area and San Francisco Bay. And so, of course, the San Andreas fault in the red colors there, that's your main fault. But again, it's all about the fault zone. So all of these other faults here in the purple and yellow and green and white, blue, those are part of the fault system. So what I'm going to point out is look for the northern Calaveras and the central Calaveras faults there. Okay, so that's where Hollister is. And that's not the most dangerous part of California. I wouldn't be scared to live in Hollister because I know that they have fault creep there. I will tell you a place I would be a little scared to live would be anywhere near the Hayward Fault. So you see there the North Hayward and the South Hayward faults. And again, I think that the next large quake in the San Fran area is going to be due to the Hayward Fault. It's been quite a while since they've had an earthquake of any size, decent size, on the Hayward Fault. Okay, just for fun, not on your exam, at the Mariana Trench. Remember the Mariana Trench is the deepest part of any ocean on our planet, and it's an ocean-ocean subduction zone. And why is it so deep there? Because the Pacific plate there is very old and a lot more dense than the Philippine Sea plate, and so it's subducting at a very steep angle, giving us the deep trench. So in theory, the Mariana Trench should be a dangerous plate boundary, and it should be capable of producing very large quakes like 9.0 to 9.5. But what we actually see is we don't tend to have very large quakes at the Mariana Trench, that subduction zone. They tend to happen more often and they're smaller magnitude. Why? Again, it's serpentine, this metamorphic mineral, greenish color, fibrous asbestos-formed mineral. And the parent rock was an ultramafic parent rock, like a peridotite, made with a lot of olivine. So sometimes you just get lucky, and if you have serpentine there at your plate boundary, then you are likely to get fault creep. So they have more frequent but smaller magnitude quakes at the Mariana Trench. And a really interesting thing is this last bullet here. There are mud volcanoes on the overrunning plate erupting serpentinite mud. Seismometers and seismographs are not on your exam, but we might just take a quick minute to take a look at these. So the seismometer is the machine that records ground motion caused by earthquakes and other things that shake the ground. The seismogram, sometimes called seismograph, is the printed record of the arrival of our P waves, S waves, love waves, and Rayleigh waves. So earlier we looked at an old school seismometer with the rotating drum of paper. Well, of course, we've come a long way since then, and these are what our modern seismometers look like. So on the left is a close-up image, and clearly somebody here, maybe from the USGS, is going around to the schools and talking about earthquakes with the school kids. I think that'd be a fun job. On the right, there they are installing a seismometer. Now, in this one here, they've not installed it to a very deep depth. Sometimes we'll drill down and install them on bedrock. Anyway, and of course, these things are all electronic now, and they send instantaneous real-time data via satellite to scientists at the USGS. And of course, it's being encased in a drum, and it's going to be watertight so that the elements are not going to mess up the computer portions of this. And if you ever get a chance to watch Dante's Peak, there's going to be a scene where they're up on the flanks of the mountain installing a seismometer. Here again is a drawing and an image of an old school seismometer, and then showing that we are more likely in a lot of cases to actually install these to some depth there in the subsurface and not right at the surface. There's our old school seismometer again. We actually looked at something very similar to this before. I'm just going to remind you quickly to take a look at your surface waves here. They have the greatest amplitude in ground shaking, and they're right beneath our feet, right beneath our buildings and bridges. So again, the surface waves are causing a lot more damage than the PNS waves. Okay, measuring the size of earthquakes. This is not on your exam, but we'll just quickly narrate these slides anyway. So we want some idea of the intensity of the earthquake, as in how much shaking do we have, what kind of damage do we have. That's modified Mercalli, which is kind of old school. And then, of course, the more modern is the magnitude, measuring the amount of energy released. And there's the old school Richter scale, and then the more common moment magnitude. Although often when they're reporting these on the news, they're going to go ahead and say it was a 5.9 on the Richter scale. It's not really the Richter scale anymore, but that's okay because everybody kind of knows what they're talking about. They've heard of Richter scale before. So the Richter scale is a logarithmic scale, and it's measuring the amplitude of ground motion. So what's interesting here is every whole number increase, like from 1 to 2, represents 10 times the amplitude of ground motion. Okay, now if we went from a 1 to 3, how many times amplitude of ground motion would that be? In other words, would we be adding the two 10s together, or would we be multiplying the two 10s together? This is something I like to ask when we're in class together, which is, of course, not happening much these days. Anyway, so if you answered we're going to multiply those 10s together, you are correct. In other words, a 3 is 100 times the ground shaking of a 1. And a 4 is 1,000 times the ground shaking of a 1. And a 5 is 10,000 times the ground shaking of a 1. And a 6 is 100,000 times the ground shaking of a 1, and so on. So you see there, when you start to get to those numbers, 5.0 and above, you're looking at some really large amounts of ground motion. Okay, so here's just an example there on the first bullet. We kind of went through some examples on the previous slide. Just know there's no upper limit to the Richter scale because, who knows what we're going to see. And the meteorite impact could go way beyond the 9.5 that we've seen on this planet from an earthquake. And when it comes to the energy released, it's even worse. Every whole number increase represents 31 times the energy released. So a 2 is 31 times the energy released of a 1. That means a 3 is 31 times 31, or 900 and some times the energy released of a 1. Okay, you can pause and look at this if you would like to. We're going to skip it. Okay, so moment magnitude is the more modern version of Richter scale. This is really what we use these days. Although again, on the news, they're not going to say this was a 6.0 on moment magnitude. They're going to say Richter scale, but it's moment magnitude these days. So the old Richter scale only looked at the amplitude of body waves. So moment magnitude is going to look at the amplitude of body waves and surface waves, which is good because remember the surface waves have a larger amplitude. We're also going to look at some of the after effects, okay? So we are going to try to determine how much slip occurred along the fault during this earthquake. We will also maybe take into account the characteristics of the rocks that ruptured. If the earthquake occurred in very strong rocks, we might move that number up a little bit. If that earthquake occurred in very weak rocks, like you might have on the Calaveras Fault, we might move that number down a little bit. So this is why most of the time, not always, but especially in our larger quakes, the first number they give you, it may not stay there. Okay, they might initially say it's a 9.0. And then a few hours later or the next day, they might change it to 9.1 because, not only are they looking at the amplitude of body and surface waves, but again, they're going in and looking at the after effects how much slip occurred, and looking at the nature of the rock. So we could say that the moment magnitude is a much better descriptor than just Richter scale. Okay, now modified Mercalli. So how do we have any idea how big earthquakes were that happened in the past? So here we don't necessarily mean paleoseismology, but say 1800s. We definitely had people and language and written language and scientists and modern society and smart people running around, but we didn't have the instruments yet to measure the amplitude of ground motion. Okay, so what you use for those older earthquakes is this here, the modified Mercalli intensity scale. So this does have an upper limit. It runs from 1 to 12, and it's based on what happened during the earthquake. You know, how much shaking did you have? What kind of things were knocked over? What kind of buildings were destroyed? It's based on, you know, so you can go into the location afterwards and study these things. It's also based on eyewitness testimony. People that lived through it will be interviewed and describe what they saw, what they went through, okay? So let's look at a couple of these. And I recommend pausing on this and reading through these. It's actually really interesting. Okay, so let's look at some of these. How about a 3? Felt noticeably indoors, especially on upper floors of buildings. But people may not recognize it as an earthquake. Maybe they think it was just a train going by that had a lot of heavy stuff on it. How about a 6? Felt by everybody. Lots of people might be frightened and run outdoors. Some heavy furniture moved. You might have some damaged chimneys, cracks, some bricks falling out of chimneys, damaged plaster. How about an 8? Damage is slight in well-built structures, but considerable in poorly built structures, like unreinforced masonry. You might have chimneys falling, smokestacks falling, monuments and walls falling. How about a 10? Some well-built wooden structures destroyed, and they do better than the brick. Most masonry and frame structures destroyed, ground badly cracked. Wow, an 11, bridges destroyed, few structures remaining, especially if they're masonry, broad fissures open in the ground. 12, total damage, visible waves seen on ground surfaces, that's your Rayleigh waves, objects thrown up into the air. So this is what we would use, say, for the 1886 Charleston, South Carolina quake, to some extent in the 1906 San Fran quake, the 1811-1812 New Madrid earthquake. Okay, so here's your modified Mercalli scale being compared to the modern Richter scale. Actually, it might be compared to the, I think it's compared to the modified Mercalli, or sorry, the moment magnitude scale. Anyway, so notice that the 11 and 12 correspond to an 8.0 and up, which are considered great earthquakes. A 10 on modified Mercalli corresponds to a 7 on Richter, a major earthquake, and so forth. So you might pause here and take a look at it. It's pretty interesting. You can pause here and look at this if you would like. Annual earthquake occurrence. As in, you know, your typical for the magnitude. How many you're going to have per year, what you might expect, and some examples if you have them. Foreshocks and aftershocks not on your exam. Foreshocks, smaller earthquakes that may precede a larger earthquake. Okay, the problem with foreshocks is this. People sometimes ask, can't we use foreshocks to predict earthquakes? Well, no, we can't, because the vast majority of smaller earthquakes are not foreshocks. It's just a smaller earthquake. You don't know that it's a foreshock until you have a later, larger quake happen. And of course, at that point, it's a little too late to recognize that foreshock, you know, meant an earthquake was coming. Basically, you can't tell when the smaller earthquakes are foreshocks. Aftershocks always happen after a larger quake, and they tend to be smaller than the main shock, but sometimes they're almost as big as the main shock. And the aftershocks, we think they're due to the stress regime on the fault being changed, modified as a result of the main shock. And it could be that you add new stresses on nearby faults that are in close contact with the main fault. And of course, the scary thing about the aftershock is that it hampers rescue efforts. So you have a building that is only partially collapsed, and you have rescue workers in there trying to get people out that are still alive. And then here comes a 5.2 aftershock. And before the first quake, that 5.2 wouldn't have been a big deal and wouldn't have necessarily brought that building down. But now you've got some people alive in there, and you've got rescue people in there risking their life, and then that 5.2 might just bring down all the rest of the building. And that could be very tragic. Earthquake destruction. You can pause here and read through this on your own. Tell you what, I might ask you to write down that last bullet there. This is something we've mentioned before, we'll probably mention again. But here's the thing. The worst kind of structure to be in during an earthquake is an unreinforced masonry building. What does that mean? It means brick, concrete, cinder blocks. Buildings made from that were not designed to earthquake standards and have not been retrofitted are just terrible. I wouldn't want to live in even a reinforced masonry building. I wouldn't want to live in, say, the West Coast where you have more earthquakes. The best building to be in is a wooden house, especially if it's anchored to bedrock, and if it's single story, that's the best. Okay, so other hazards associated with our earthquakes, meaning other than ground shaking and displacement. Okay, landslides. So, the ground shaking is not necessarily all you have to worry about. Shaking can cause steep slopes to fail, and that can bury houses and people. Sediment liquefaction. So when it's not COVID and we come to class more often together, there is video of sediment liquefaction from Japan that I like to show. I can guarantee we're not going to have time for that. What I would ask you to do is go to YouTube and type in Japan earthquake 2011, I think it was 2011, liquefaction, and then take a look at some of those videos. They're just really cool. So what happens in the case of liquefaction is if you have unconsolidated sediments that are saturated, meaning that you have water, high ground water level, high water table, you got water in the pore spaces, that's a terrible thing to build buildings on, because when you shake that material, it moves and flows and becomes a liquefied slurry. So liquefaction can topple buildings that otherwise wouldn't have fallen down. So if you copy and paste that link, it may or may not take you to an animation for liquefaction. We're not going to read through this, but you can pause on the slide and read through it if you're on your own. If you want to, it kind of tells you how, if you go to the beach, you can model liquefaction for yourself down there in the surf zone where the waves are coming in and going out. And then that drawing on the left kind of shows what's happening to the sediments there when liquefaction occurs. So over on the left, you've got sand grains here, unconsolidated sand grains. You got a lot of pore spaces, but they're all filled up with water. When you shake that material in an earthquake, you lose the grain-to-grain cohesion, you lose that friction, and that material is going to flow. And again, that can topple buildings. I highly recommend, if you go to the beach, that you do this experiment here and model liquefaction for yourself. So these things here that look like little shield volcanoes, I know in this image they're labeled as sand volcanoes. Some of us prefer to call them sand blows. So the drawings down below show how this happens. So you've got some well-packed soil on top, and below that you have loose, unconsolidated sand and a high water table. And then you shake this material, and you end up with this material below the soil being under pressure, and it's basically going to punch through or kind of erupt through the soil and deposit these things that look like little volcanoes, and those are sand blows. And the cool thing about sand blows is, well, they're evidence of liquefaction, and therefore they are evidence of large earthquakes. So an example would be out in the area of New Madrid, Missouri, where you have the Reelfoot Rift, a failed rift, that we had large earthquakes there over several months between, say, December 1811 and February 1812. And there weren't a whole lot of people living there, and yes, they had written language, but we didn't have seismometers. I don't think we had modern photography yet, or if we did, normal people that weren't rich couldn't afford them, so there's not a lot of pictures. But sand blows formed and were then buried by new sediment and therefore preserved in the sediment record. So many slides back when I mentioned paleoseismology and how we might dig around in the sediments in the vicinity of these faults, we might look for these buried sand blows and know that we've had large earthquakes here in the past. If you click on this, I have to admit that I forget which one this takes you to. You could try it. You could copy and paste it and see if this will take you to a liquefaction video. Here is an image of these sand blows in a farming area. So again, sometimes we get lucky and these things get covered over by new sediment and preserved in the sediment record for clever geologists to go and find and be able to decipher the earthquake past in this area. So this is from an earthquake that hit Nagata, Japan back in 1964. Notice that these apartment buildings, I'm assuming they're apartments, they did not pancake. Okay, that's great. They were built to some standards. The people in Japan have good earthquake building standards because, well, they've been dealing with earthquakes and tsunamis for thousands of years, as long as they have had people living there. Anyway, but even though the buildings didn't pancake, you still have bad things happening and potential loss of life. Look at that building in the middle. It's ripped up off its foundation and just smacked over on its side, and that is because of liquefaction. Here's that image again. Okay, so we're still on this topic of hazards other than just the ground shaking. Fire. So one of the problems here, and this happened in the 1906 San Fran earthquake, is that you're going to have gas mains rupture, okay? Or just simply that, somebody's gas stove ruptures, or somebody lights a candle because it's night and the electric's out, but then the aftershock knocks the candle over. So fires easily start, and then they can be hard to put out because not only do gas mains rupture, water mains can rupture, and then the firefighters have no water pressure to fight the fire. So fires may devastate areas that were not badly affected by the quake, and this happened in the 1906 earthquake. This also happened to some degree in the 1989 Loma Prieta quake, which was also in the San Francisco area. Okay, and then of course tsunamis. Tsunamis are considered an additional hazard other than the ground shaking. So what is a tsunami? Well, it's a massive wave, much bigger than your typical wind-driven waves. And generally, they're caused by earthquakes offshore. Landslides can cause them. Large volcanic eruptions at your island nations can cause them, or meteorite impacts. So back on Boxing Day, which is a British holiday, that is December 26th, the day after Christmas, back in 2004, Sumatra. We had a very large earthquake and tsunami. The earthquake was a 9.1. We refer to this as a megathrust quake because it occurred right at the plate boundary interface. I'm going to want you to know a little something about this earthquake, by the way, for your final exam. Okay, so it was a megathrust quake, and it caused a devastating tsunami. And what you need to know is this: there was no tsunami warning system in the Indian Ocean at that time, which is why you had almost 250,000 people that died. Very sad. We do now have a tsunami warning system there because after the earthquake happened, scientists and governments from different countries all worked together and made sure they had a warning system. But there are parts of it that are already in disrepair and not working. Anyway, you had C4 offset uplift of around 10 meters. Yeah, 10 meters, 30 feet on the India plate. You had slip over as much as 1,200 to 1,300 kilometers length of the Sunda Trench, although the majority of slip occurred along the southernmost 400 kilometers of rupture. Still, that's a lot of rupture, a lot of offset. Okay, so a tsunami was generated. It hit countries all around the Indian Ocean. I believe it even, yeah, it hit countries all around the Indian Ocean. Oh, I'm sorry, it killed more than 250,000 people. So this was a record breaker, unfortunately. Killed more than any other tsunami in recorded history. And again, no tsunami warning system. That's an exam question. But we do have a tsunami warning system now. This is an image of that tsunami coming in. Now, it's not necessarily, it's not just one big wave. Okay, the waves don't have to necessarily be super tall, 30 feet tall or 100 feet tall to cause damage. The problem with a tsunami is that the wavelength is very long, so it ends up pushing a lot of water onto the land. Here's an image of the tsunami coming in. Does anybody know, and this is an exam question, I believe, it might be extra credit, what happens to the ocean before a tsunami comes in? Say you were vacationing somewhere on the Indian Ocean because you won the lottery and you can do that kind of thing. And you don't feel any earthquake, but the ocean does something weird before a tsunami's coming. Anybody have the answer? The ocean will actually recede first. It will first kind of suck out to sea. Okay, so everybody needs to know this because sometimes you are on an ocean and a tsunami's coming and you may not know it, and you're too far away to feel the earthquake. If you're on a beach and you feel an earthquake, you better get to high ground right away. If you're on a beach and you don't feel an earthquake, but you see the water going out to sea, you better get to high ground right away. So here's an image from that tsunami. Here is an image somewhere in Indonesia of the aftermath. I mean, this is just terrible. I mean, it looks like a Category 5 cyclone. That's what they call them in the Indian Ocean, a hurricane. It looks like a Category 5 cyclone hit this place. Very few buildings left standing, just complete destruction and loss of life. You can pause here and read through this on your own if you want to. Definitely not on your exam, but just kind of an interesting thing. So the scariest thing about a tsunami is it has a very long wavelength, okay? And that wavelength can be definitely greater than a kilometer. It can be a few kilometers, as opposed to wind-driven waves where your wavelength, or the distance from peak to peak, is only going to be a few meters. So what that means is that while in the open ocean, the wave height of a tsunami might be less than a meter. So a ship out there that has that tsunami wave pass beneath them may not even notice because it's very small. But then because of the long wavelength, when it starts to make bottom and getting into the shallower coastal areas, yeah, it could pile up to as high as 30 meters. I think it's incredibly rare that we actually see a tsunami wave that high, but again, it doesn't have to be that high. It could be only 10 to 30 feet high, but it's destructive and horrible, and it comes very far inland. You can pause here if you would like and take a look at tsunami generation. We don't need to write any of this down, but do know this, they have a warning system now. It took about 18 months to get one working. And just so you know, we're covered in all oceans, okay? Because back in 1960, we had the largest earthquake ever recorded at 9.5 in Chile in South America. And that made a devastating tsunami that went all across the Pacific. Well, we began then working on a tsunami warning system in the Pacific. And it wasn't completely operational until 1965. And in between then, you had the 1964 Alaska quake. But we have a fully functioning system in the Pacific. We actually have one in the Atlantic, and yes, we could get a tsunami from the Canary Islands. It could happen, and it's been upgraded, and we even have a system in the Gulf of Mexico now. Okay, I'm not going to go into detail on this particular quake. You can stop here, you can pause and take a look at this if you want to. This is just a more recent earthquake in Indonesia. Same thing here. This is not in your exam. You can pause this presentation and read this if you would like. This has a little something to do with, again, a more recent earthquake in Indonesia. Haiti. Gosh. Yeah, I might want you to know a little something about the Haiti earthquake. 10 years ago now. Back in 2010, January. It was only a 7.0, but it was a strike-slip fault, so it was a shallow earthquake. The epicenter mostly on land. There was a little bit of compression. It produced a small local tsunami, but that wasn't the problem. The problem was that this 7.0 shallow earthquake brought down many buildings because they really have no building standards in Haiti. It's a very poor country. There's a lot of corruption. Even if you tried to enforce standards, probably nobody could build to those earthquake standards. So even without having a big tsunami, it killed almost 250,000 people. So here's an image of here's an image from the Haiti quake. What I want you to notice, well, notice that the buildings on the right side of the street are collapsed. The ones on the left are not. The ones on the left, we have to assume, maybe are newer and built to some kind of standards. Notice these buildings on the right that have collapsed are made of concrete. So this is your unreinforced masonry. Here's another image from the Haiti earthquake. Wow, this is pancaking at its worst. So look at that building. Again, unreinforced masonry. This is a death trap. And then look at those horizontal slabs. Those are floors and ceilings of, different stories. And you had clearance of probably, at least 8 feet in between. And they're now all smushed together, pancaking. This one here, we can skip. You can pause and read it if you want to. This is a more recent earthquake in Chile. Same thing here. You can pause and read it if you want to, but you don't have to, not on your exam. We will take a quick look at this one. This is what your surface waves can do. Look at this road. Okay, it's not supposed to be this way. Now the good thing is this appears to not be a bridge or overpass, but that road is all busted up from the surface waves, Rayleigh waves and love waves. We will take a look at this image. This is from a more recent quake in Chile, I think 2010. This is a raised roadway, okay? And notice where your failure is occurring. Okay, it's occurring where you have different pieces of road deck that have been attached and connected where you have those support columns. And what you're going to notice are all those gray spaghetti string looking things. That's rebar, okay? So rebar is metal that's put into concrete, and it's meant to give it strength. All right, and sometimes students ask me, what about the rebar? Doesn't that help? And the answer is no. What the rebar is good at doing is supporting the weight of the road deck above and all the traffic on it. The rebar is not very good in an earthquake when you shake that material. So this is pretty common to see these things fail where you are attaching road decks to the support columns. This one is also not on your exam, so if you want to pause here and read it, you can. Relatively recent earthquakes that happened in New Zealand back in 2010 and 2011. Now here's an image from the Christchurch earthquake in 2011. If you look at this collapsed building, do you get some idea of what kind of building this was? Okay, I'm pretty sure this was a parking garage. All right. Parking garages are the worst buildings by far to be in an earthquake. They're very dangerous. It's what we call soft story construction. They're just not very strong and they don't hold up well in an earthquake. If you are ever in a parking garage anywhere in the world and you feel shaking, my advice is if you can get yourself to the stairwell, do that, because the stairwells, as we see here in this image, tend to hold up a little bit better. Here's another image from the Christchurch earthquake in 2011. This is pancaking. Each of those round things was somebody's balcony to sit on and drink coffee in the morning or maybe wine in the evening, and now it's just a death trap. Japan. I do want you to know a little something about the Japan quake for your exam. This is back in 2011. It was a 9.0. Okay, so this is another megathrust quake, meaning that it happened right at the plate boundary interface, which is very, very dangerous. So this is, well, I guess currently we would consider that maybe, well, it's a subduction zone. We'll just put it that way. Technically, I guess that'd be an ocean-to-ocean subduction zone. It's just that we have a very large set of islands that has formed there. Some interesting things here. Coastal subsidence of 1 meter, sinking of a meter because of liquefaction. And yet part of the island near the epicenter moved east by almost 5 meters, and close to the epicenter you had uplift on the overriding plate of about 4 meters. And yes, a devastating tsunami was produced. You had uplift of the fault trace by as much as 30 to 40 meters. That is not a typo. You had rupture along 300 kilometers of that subduction zone. That's huge. Even with a tsunami warning system, the death toll reached almost 21,000 people. So here's the problem. The problem is that the epicenter was so close to land that they sent out the tsunami warning, but you only had about half an hour, and that wasn't enough time to get everybody to safety. Here's an image from that tsunami 9 years ago. If you click on this image, or copy and paste into YouTube, it may or may not take you to the tsunami video I like to show in class. And if it doesn't, then just go to YouTube and type in Japan, earthquake and tsunami. Oh, this is different. Yeah, this is not the liquefaction video. That's right. I usually would show 2 videos. This is tsunami video. That's another thing you can do if this copy and pasting here doesn't work. You know, sometimes the links kind of change. You can just go to YouTube and you can type in Japan, earthquake and tsunami, 2011, and there's all kinds of video of the tsunami. Okay, you don't need to know anything about Turkey for your exam, but it's a dangerous place to live. It's a microplate, a microcontinent. What that means is that the boundary of the country is also the boundary of a microcontinent. And that means that they are surrounded by plate boundaries. So the worst quake in my lifetime here was in 1999, and this was the North Anatolian Fault, a right lateral strike slip fault very similar to the San Andreas, but it killed 17,000 people and injured 50,000, which is a much higher death toll than we would have on the San Andreas. And of course, the difference is all about the buildings. So Turkey also, they don't have as much money as the United States or California. And they got a lot of old buildings, and they just, they don't have the building standards that we have. This slide here, we're going to skip. This was a more recent earthquake in Turkey. You can pause and read through it if you'd like. Aha, New Madrid, Missouri, 1811 to 1812. You're going to need to know a little something about this for your last exam. So this is the Real Foot Rift, which is a failed rift. We talked about it briefly in plate tectonics. This is in the region of New Madrid, Missouri, sometimes referred to as the New Madrid Fault Zone. So the scary thing here is there were several large quakes from December 1811 through February 1812, and 3 of the quakes were estimated to have been around a magnitude 8.0. That's crazy. So these began as high-angle normal faults when North America experienced extension between, say, 500 and 300 million years ago. But they're now being reactivated as strike-slip faults due to compression as the North American plate slowly moves west-southwest. It's a very dangerous place to live, honestly. And there's a lot of old, unreinforced masonry buildings there. And it's just waiting to have an earthquake. And paleoseismology tells us that we have earthquakes here roughly every 300 to 500 years. We have large quakes. It's been 200 years. Is another set of quakes going to Large quakes coming? Absolutely. It's just a matter of when. And they do from time to time have smaller quakes. So, on this slide, if you want to, you can pause and read through it. It's basically what I mentioned on the previous slide, a little bit of background here with the failed rift. It's really pretty interesting stuff. Anyway, if you take a job anywhere near New Madrid or St. Louis, Missouri, or Memphis, Tennessee, please try and not live in an unreinforced masonry apartment building. So here is a map of earthquakes, epicenters, and magnitudes in the 1800s, and the three really big dark red circles are the largest quakes. So this stretches quite and kind of follows the Mississippi River. Everybody see that? Okay, and that's kind of interesting because, well, the Mississippi River is kind of following the outline here of our failed rift. So, using modified Mercalli, based on what people had to say about the quake at the time and wrote it down, we can make an isoseismal map. So you'll note it was an 11, okay, so not quite the largest, but again, similar to an 8.0 or above. And of course, as you move on outward, the shaking gets less. But I'm going to point out my hometown, Charleston, West Virginia, that they'd have felt it pretty good. They'd have felt it like a 6. Our part of North Carolina, we'd have felt it pretty good. We'd have felt it like a 5. And notice that this map is drawn to the east only. And they haven't drawn it to the west. Okay, so does that mean that they didn't feel shaking to the west? And the answer is no, it does not mean that. Okay, what it does mean is that we didn't have a whole lot of population west of here at that time, and I guess we just don't have enough information about what it was like to draw this map west of here with any accuracy. Charleston, South Carolina, I'm going to want you to know a little something about this earthquake. 1886, it was a 7.3. You don't have to remember the magnitudes necessarily. But this is another intraplate quake. Okay, so the New Madrid, Missouri earthquakes are intraplate, meaning it's not a plate boundary in Missouri, and yet they have large earthquakes from time to time. Same thing with Charleston, South Carolina. It's not a plate boundary. Our nearest plate boundary to the east is way out there in the middle of the Atlantic, at the Mid-Atlantic Ridge. Okay, so what's going on in the case of Charleston, South Carolina? It's a fault. It's a left lateral strike slip fault called the Woodstock Fault. And we don't know as much about it as we do the New Madrid area, but clearly it's an old fault, perhaps related to the assemblage of Pangea and or breaking apart of Pangea, and the faults just don't heal. They can become reactivated. So Charleston, South Carolina is earthquake country. Here's an isoseismal map for Charleston. So this one was a 10 on modified Mercalli, not the largest, not quite as big as New Madrid. But again, you can kind of see what the shaking felt like further away. Something I love to point out. Look at North Carolina. Look at how they have Norfolk, Virginia in North Carolina. That's hilarious. Norfolk is up in Virginia, but that's okay. Our part of North Carolina would have felt it pretty good, would have felt it like a 5. Now, something I want to point out is let's go west. And let's go out to the New Madrid fault zone, okay? So surrounding the New Madrid fault zone, they would have felt it as a 4 or a 2 to a 3. But there in the area of the New Madrid fault zone, it goes up to a 5 and a 6. And that's because, well, the rock there's pretty weak because you have a big fault zone there. So I never can find images, any photos that people took from New Madrid, but there are several from Charleston, and there's a few of them in this image. So you'll notice bricks falling out of buildings pretty easily, unreinforced masonry. You can stop here and read through this if you would like. On this one here, I also recommend pausing and reading through this if you got time. It's interesting stuff, but we're going to move on. Same thing here. You could pause and read through this. It's interesting, but we're going to move on. By the way, every dot on here is an intraplate quake. We don't have any plate boundaries here in this part of the United States, only on the West Coast. Here's the doll's house effect. You lose a lot of your brick outer walls and you can look in. This building clearly is no longer stable or safe, and you're not just going to go in there and live in it. And you really can't just repair. I think you got to tear it down and start new. This is another slide that I recommend pausing and reading over this. This is an image of Reelfoot Lake. This lake did not exist until one of the large 8.0 earthquakes. This is the earthquake that happened in February 7th of 1812. Yeah, the Mississippi River actually temporarily dammed and ran backwards, and a new lake was formed, and that lake is still there. Okay, 1906 San Francisco. Do I want you to know something about this quake? Absolutely. It was a magnitude 7.9. That's huge for a strike slip fault. Because it was strike slip, it definitely had a very shallow focus. You had, shame on me. I haven't looked at these slides in a long time. I think a couple of times I may have mentioned having slip on as much as 600 of the 800 miles of the San Andreas, but no, it was more like 300 miles of the San Andreas fault. Still, that's a lot of offset. Average offset was 8 to 12 feet in one earthquake event. In some places, offset was as high as 20 to 28 feet in one earthquake event. And the earthquake caused a great fire that damaged parts of the city that weren't all that badly damaged by the earthquake. On the left there, you see a nice ground rupture image, and you see a lady standing there looking at it. Over on the right, it doesn't show you here, but that offset is 8 feet. Okay, and that happened in one earthquake event. Imagine witnessing that. How crazy would that be? This is what your ground roll railways can do. You have a very heavy train engine and cars that have just been knocked over like they were children's toys. All right, so the images we will quickly look at from San Francisco, you're going to see some recurring themes. You're going to see brick walls knocked into the street, and you're always going to have that fire because, again, that fire raged out of control, and it was hard to fight it because water mains had broken. I'm going to point out a building over there on the left that looks to be kind of like a light tan color in this black and white image. That doesn't look damaged at all, but also it looks like it's made of wood, not bricks. Here's a toppled house on Howard Street. Yeah, foundation's all messed up. You don't just go back in there and live again. These are two different views of the same location, okay? So the one on the bottom is what this street looks like today. Everybody thinks everything is just fine. And then, of course, the image on the top is that same street back then in 1906 after the earthquake happened and the city was burning. Okay, so here again, another image. What do you always see? You see the fire raging out of control in the background, and you see unreinforced masonry collapsing. Oh, here they tell you, 8.5 feet. Okay, 8.5 feet of offset there on that fence. And then you see some offset in an orange grove up there as well. Okay, other notable earthquakes. Yes, I want you to know something about the 1964 Alaska earthquake, Prince William Sound. 9.2, probably the second largest quake that we've seen on this planet. Shaking lasted for 3 or more minutes. That's terrifying. This was ocean to continent subduction zone. We could also think of this as a megathrust quake, meaning it happened at the plate boundary interface. And it produced a devastating tsunami. Uplift of roughly 11.5 meters. That's crazy. Okay, Chile, 1960. Yes, you need to know this for your exam. The largest earthquake ever recorded in modern times. 9.5. Chile, west coast of South America, 1960, ocean to continent subduction zone. Again, this was a megathrust quake right at the plate boundary interface. Devastating tsunami. The death toll seems really low here, but I'm going to guess that they just maybe didn't have great reporting and that don't really know. Interesting thing there on that last bullet. Okay, rocks do not have infinite strength. Okay, stick-slip behavior, eventually the stresses overcome the strength of the rock. So I personally don't think we'll see an earthquake with a magnitude above a 9.5, or certainly I don't think we'll get to a 10.0. Meteorites, however, could knock it off the charts. This shows you in red, that's the epicenter of that earthquake. And then that image there to the left, we're going to see that blown up on the next slide. Look at this, okay? So this was a subduction zone earthquake, so you are going to have uplift of the overriding plate. But when you're near the coast and you have unconsolidated sediments and a high water table, you get the opposite. You have things, subsiding, sinking, dropping down. This is downtown Anchorage in the 60s. And yeah, look at that. That entire portion of street and buildings and cars all just dropped down by well over, I guess, 10 feet. I'm not sure where this image comes from, to be honest. But what's important here is this is liquefaction that has lifted this building up off its foundation and tipped it over on its side. So this is back to Alaska. And who knew that they built their house in the fault trace, but they did. And now you have great vertical offset here. And notice that the house has been torn in two, but it hasn't collapsed. In other words, the people inside should have lived through this. What does that house appear to be made of? Wood. Here we have a school building. I'm assuming it's a school. It looks like it, and that looks like a jungle gym on the left. Anyway, yet again, built on a fault trace. Lots of vertical offset here. Many, many feet of offset. School building's been torn in half, but it hasn't collapsed, and nobody had to die in this building in this quake. What does it look like it was made of? Wood. I like to call this image chaos. Okay, I mean, just look at that broken up ground. Gosh, that's terrible. Do you see the roofs of the houses over there, kind of in the middle to the right, all knocked off their foundation? Imagine if school kids were walking through here to go to school when that earthquake hit. And yes, they would live through this being outside, but it would just be really hard to deal with, I think, emotionally. Here's another image from the 1964 Alaska quake. So we're going to look at, in this slide and the next one or two slides, this was a neighborhood known as Turnagain Heights, and what you had happen here, buildings built on unconsolidated sediments and high water table, and you shake it and you end up forming a whole bunch of normal faults very quickly and hanging walls sliding down, and it destroyed the houses in the neighborhoods. Here's an image of Turnagain Heights from the air, and it's just all in disarray. So here are some more images from Anchorage. That one on the top left we've seen, the one on the top right's pretty interesting. I mean, how do you even begin to go in and repair? I mean, the ground is no longer level. I mean, I guess you bulldoze everything and you try to level things out and rebuild the roads and everything. So that image on the top left, again, that's Turnagain Heights. That was our Alaska quake of 1964. On the bottom right is Chile. So, Chile, it was the 60s. We might have classified them a developing country back then. Just not a whole lot of photographs from that earthquake that I've been able to find online. Here's an image from Chile. Talk about the doll's house effect. I mean, at least the whole thing didn't collapse, but you lost, like, really most of the outer walls of this particular building. And then here's another image from Chile. So the good news is that a lot of the buildings in this photo are still standing, but the stuff behind him is just completely collapsed. And what's it made of? Concrete, unreinforced. Bunch of rebar sticking up out of the ground, not doing you any good. I might recommend pausing on this slide and taking a look at it when you've got some time. We're going to go past it. It's just kind of discussing some of our most notable earthquakes that we've had. Okay, Loma Prieta, 1989. You need to know a little something about this for your exam. It was a 6.9. You don't really have to know the magnitudes for most of these quakes, but I'm going to want you to know that this was this earthquake was related to the San Andreas fault system. It has a nickname. We call it the World Series earthquake. And that's because both San Francisco teams had made it to the World Series. Okay, that's amazing. First of all, two teams in the same city playing each other in the World Series. This happened in October, I believe it was October 17th, and they were playing a game at the time that it hit, and they said that that helped to save lives because they had a lot of bridge and double-decker roadway collapse, and that's where a lot of the deaths were. And they said that certainly if the game had not been playing, there would have been more people on the roads. And then more people would have been killed. So the fact that that game was playing and people were at the stadium or at home watching, less people were killed. But there were still several dozen people that were killed. And the Marina District, which was 100 kilometers away, was very badly damaged, more so than some places that were closer to the epicenter. And it's because it was built on fill, meaning that they took some of the rubble from 1906 earthquake and they put it out there in the Bay Area to create more land, create artificial land, but that land was very unsafe. And then they went and built, you know, condos and apartments on it. And there were people that got killed there as well because there was a lot of collapse. So, you can pause here and read this on your own time if you would like to. We're not going to take time for it. You can pause here and read about this on your own time if you would like, but we're not going to take time for that. So here are some images of destruction from the Loma Prieta earthquake. There's the Oakland Bay Bridge up in the top left. Over on the right is the Cypress Viaduct. And you see that that double-decker roadway has pancaked and has killed several people, and that rebar again didn't do you any good. Here's an image of, I believe, the Cypress Viaduct from above, and just the terrible destruction, the pancaking, and now you've got engineers and construction workers up there, you know, well, they're going to study it first and figure out why it failed so miserably, and then when they figure that out, they'll tear it down and build new stuff, new roadway there. I recommend pausing here and reading through this when you have time. It's talking about an early warning system. No, this is not predicting earthquakes. It's just saying that when one starts, if they can instantly send a warning out on people's cell phones, then, you know, if you're far enough away from the epicenter, maybe you've got time to run outside, or the surgeon can take the scalpel away from the person they're operating on, and, you know, maybe you can save some lives. Here's our image of a nice police officer taking a look at, I believe this is the top of the, I call it the Oakland Bay Bridge. And these people have already escaped, but this is really scary stuff here. This is not the first floor of this building, okay? This is in the Marina District where everything was built on fill and failed miserably with liquefaction, and you've got pancaking, and now you have not the first floor of this building, kind of down at ground level, and it's also, you know, smushed this car that was parked beside the building. Just terrible destruction. This is soft story construction where your bottom floor is parking and then you build living quarters or office space above. It's a horrible design, and these things are just destined to fail. This whole thing is unsafe, and they'll have to tear it all down. This just shows quickly that, gosh, are they showing the Marina District? I don't think they're showing the Marina District here at all. Anyway, it's showing you where the epicenter was for that particular earthquake. Okay, other notable earthquakes. You're going to need to know something about the 1994 Northridge quake, 6.7, blind thrust fault. I want you to know that. This was not directly related to the San Andreas fault. It was a blind thrust fault. Maybe write down the last two bullets here. You might have to pause because I'm going to go to the next slide soon. But unreinforced masonry, again, the most dangerous type of building in an earthquake. Wooden houses anchored to foundations are the best. So this Northridge quake, a blind thrust fault, we didn't know it was there prior to this earthquake. It did not have small earthquakes to alert us. Several of the people that were killed were all living in the same apartment building. And it was unreinforced masonry and a very bad design, and it pancaked and it killed a lot of people. This particular quake also killed a few dozen people. So images from the Northridge quake. Let's take a look at that image on the left, and I'm going to tell you a quick, sad story. I remember this. You know, I'm older than you guys. I was definitely, you know, a person, an adult, really, in 1994. I remember hearing about this on the news. The earthquake happened, this one, in the middle of the night, and there was an off-duty police officer who rode a motorcycle, and one of the chips, I guess. And anyway, he did what, you know, he thought was the right thing to do. And he got on his motorcycle and he headed out because he's going to go help with this earthquake. And the power's out and you don't have street lights. And he came up on something like this and he couldn't see it because it was dark. And he and his motorcycle flew off the end of it. And of course, he did not survive. Look at that image on the right. And imagine being stuck in that middle part. Okay, so you're lucky it didn't collapse. But now you're hoping that they can get helicopters in there and get you out before an aftershock brings it down. This is soft story construction again. Okay, so the buildings on the left were not constructed as well as the buildings on the right, clearly. And that part that has flattened and collapsed, that is a parking area, likely, and a very bad design. So here's some images from the 1994 earthquake, damage from above. So again, these double-decker roadways, raised roadways, where are they most likely to fail? It's where you have a support beam, a support column, and then you attach two sections of road deck to it. And again, the love waves, the side-to-side surface waves, are most responsible for this kind of collapse here. Here we have some pancaking of what appears to be, I'm guessing, apartment buildings. This is 1994 Northridge again, and this is a more up-close view of that failure that you have there where you put the two bridge decks together. And I'd say that people in this car probably walked away from this because the cab is not crunched in, but they're going to be traumatized, that's for sure. Here's a map of where this earthquake happened. You see that epicenter there in the star. You can pause here and read through this if you would like. I recommend doing that. You can pause here and read through this as well. I recommend that. Same thing here. You could pause and read through this, but we won't take time for it. Here's an image from the 1906 San Fran earthquake. Even back then, not having quite as many people living in North Carolina, there were still an estimated 3,000 people that were killed. And of course, many buildings were destroyed, and some buildings, of course, were destroyed by fire and not the earthquake. This is another image from 1994 Northridge. Here is a map of, again, this is the San Andreas Fault System, focusing on the San Francisco area. I recommend pausing and reading through this. This is kind of interesting. Okay, so kind of giving you an idea of which parts of the San Andreas main fault haven't erupted in a while, or sorry, haven't produced an earthquake in a while. So the southernmost section, this is something that's being watched, has not had a major quake in 300 years. I'd say we're overdue. They're in the, and they're labeled in the red, number 4, in the green, number 3. We had the 1857 Fort Tejon earthquake. We also had a more recent earthquake, like very recent, like within the past year or two, in that area, but maybe to the east of that. The central section, well, this is a short section here involving the Calaveras Fault, so less likely to have a major quake here. And then, of course, you've got the northern section, and the northern section has already proven itself capable of producing a large quake, as we had a 7.9 back in 1906. Here's another image of the Cypress Viaduct. So this goes back to the 1989 Loma Prieta quake. There were people, living nearby, and their structure didn't collapse and didn't burn, and they'd go out and, find a ladder. They had a ladder in their garage and climb up and crawl in there and try to see if they could rescue any survivors out of cars. And, they're risking their life when they do that. It's very noble because an aftershock could bring that down. Look at how damaged it is already. And there's a close-up view of that. Again, there's your rebar not doing you one bit of good during an earthquake. I think this slide is a repeat, but again, it's some notable earthquakes, and you can pause and read it if you want to, or skip it. We are coming to the end of this, and that's good because it's going to take a very long time for this to save and even longer for it to upload to YouTube. That's okay. Just some interesting things here you don't need to write down. So, Mexico City, back in 1985, this was a huge quake, an 8.0 that did a lot of damage, but we learned a lot from that earthquake. We also learned a lot from the 8.8 in Chile in 2010. So we discovered some things here, not on your exam. Buildings between 10 and 20 stories that were on unconsolidated soils were more likely to collapse. And it has to do with resonance. So each structure has a natural resonance, meaning how it's going to shake in response to ground shaking. And if you have these structures built on that unconsolidated sediments, and especially with a high water table, so you're already at risk for liquefaction, but these unconsolidated sediments amplify ground motion. I don't think I've mentioned that yet in this presentation. So these are just very dangerous places. And what happens is if the soil, if its natural resonance of vibration is the same as the building's natural resonance, then these buildings are likely to collapse. And apparently if they're between 10 and 20 stories, they're even more likely to collapse than if they were less than 10 or more than 20. So here are some images from, well, the one on the right is from the Mexico City quake in '85, and the one on the left is from the Chile quake in 2010, I believe. But we also saw the same thing in the Sichuan province quake that happened in 2008, and that was a devastating quake that killed thousands of people. It was a 7.9. And on that notion, again, this is just for fun. It's not on your, or for interest, I should say. It's not on your exam. 2008, not that long ago, a 7.9. So this was a thrust fault, and I mean the death toll here is horrible. I mean, no tsunami, but still anywhere from 70,000 to 90,000 people killed. Estimated over 5 million buildings collapsed and 21 million buildings damaged. This tells you that, this is an area where the building codes were not all that great. And then here is a portion of the earthquake poster that the USGS prepared after the 7.9 quake. Okay, so what about the rebar? Well, again, it's not meant to protect during shaking. It doesn't do that. It holds up the weight of the bridge deck and the traffic above. They have discovered that if they put more rebar in these columns, while they won't necessarily keep that structure from collapsing, if they have more rebar than normal, it might at least keep the structure from completely failing. And then you hopefully have time to get the survivors out. So if there's not enough rebar, or if it's just not strong enough, the structure will fail. And we've seen that a lot in the older structures. This is a potential extra credit question. All right, east of the Rocky Mountains, you can feel the earthquakes much further away from the epicenter than you can west of the Rockies. As a matter of fact, perhaps you might feel the earthquakes up to 10 times the distance away from the epicenter than west of the Rockies. And it has to do with the fact that east of the Rockies, you've got stable, old North American continent. And then west of the Rockies, you have a bunch of accreted terrains. So the accreted terrains are actually going to absorb that earthquake energy quicker. So while you expect larger, more devastating quakes on the west coast, they're not going to feel the shaking quite as far away from the epicenter as we do here in the east. Okay, the rest of this stuff is interesting, and I'm not going to narrate it. I'm just going to click through the slides so that it'll be part of the presentation. If you have time and you're interested in this stuff, you can certainly, pause on these slides and read through it. It's a lot of fun, but unfortunately we don't have time to cover mountain building or crustal deformation because we're not allowed to teach physical geology here. We have to teach earth science, therefore we have to squeeze in weather and atmosphere, so we don't have time for this, but it's interesting stuff. So if you want to read through this, you can keep on going, and you can pause on any of these slides and read through this if you would like. It talks a little bit about mountain building. Orogeny is the term we use for a mountain building event. Again, for any of these slides, you can pause and read through these if you'd like.